Hi, hello and welcome to another session on electromagnetic field theory and waves. In today's video we'll discuss the fourth unit, that is the electromagnetic waves part 1. So let's get started. So as you can see, these are the features of an electromagnetic wave. Electromagnetic wave, it has two components. One is the magnetic component, second one is the electric component. Both of these components are mutually perpendicular to each other and both vary with respect to z direction only. Some examples of electromagnetic waves are light rays, the TV signals, radio signals, mobile signals and microwaves. So first we'll derive the expression for the uniform plane wave equation. So here we need to start with the Maxwell's equation. So this is one of the Maxwell's equation. Del cross H is equal to J plus dou D by dou T. Here J is the conduction current density and dou D by dou T is the convection current density. Now in a perfect dielectric there is no conduction current density, so this J term will be equal to 0. So in place of J, if we substitute 0, we can write this as del cross H is equal to dou D by dou T. Now we'll expand the equation on both sides, left and right sides. First we'll start with the left hand side. So explain this as the cross product del cross H is equal to AX, AY and AZ. These are the unit vectors. So put them in the first row. In the second row we have this dou by dou X, dou by dou Y and dou by dou Z. Then we have Hx, Hy and Hz. Here we are using the Cartesian coordinate system. So expand this. So we get these terms. Now one more important point is that the electric field component is along the x-axis and H is along the y-axis. So we have only Ex component and Hy component. The other two terms, that is Hx and Hz, will be equal to zeros. So in this equation, if you substitute Hx and Hx and Hz equals to zeros, so these are the terms left. Del cross H is equal to Ax into minus dou Hy by dou Z plus Ax dou Hy by dou X. Now here H is not varying with respect to X. It is varying only with respect to Z. So this second term dou Hy by dou X also reduces to 0. So this is the final equation which is left. Del cross H is equal to minus dou Hy by dou Z into Ax. Now similarly we need to expand it on the right side also. We have dou D by dou T on the right side. So we can write this as dou by dou T and expand this D term in terms of the Cartesian coordinate system. So we have three components. One is dx, dy and dz along with the unit vectors Ax, Ay and Az. So open these brackets and write them separately. We get dou dx by dou T into Ax plus the other two terms. Now equate the terms on the left side and the right side. So on the left side we have only the Ax term. So the other two terms will be equal to zeros. So write only the first term, that is minus dou Hy by dou Z into Ax is equal to dou dx by dou T into Ax. Remove the unit vectors and this is the equation left. We have a relation in electrostatics where D is equal to epsilon into E. So in place of this D we can write epsilon into Ex. That is dou minus dou Hy by dou Z is equal to dou epsilon Ex by dou T. This epsilon is a constant, so put it aside and write dou Ex by dou T. So this is the final equation which we get here. Dou Hy by dou Z is equal to minus epsilon dou Ex by dou T. Now we'll use another Maxwell's equation. Del cross E is equal to minus dou B by dou T. So this also we need to expand on the left side and the right side. So use the cross product form on the left side and we get these terms. Now here also the electric component is along x direction, so Ey and Ez terms will be reduced to zeros. So these are the two terms left. And one more thing is E is varying only along with x-axis, so it does not vary with respect to y. So this dou Ex by dou y will be equal to 0. Then del cross E is equal to dou Ex by dou y into Ax. Next, expand on the right side. On the right side we have dou B by dou T is equal to minus dou by dou T Bx Ax plus By Ay plus Bz Az. Now equate the like terms on both sides. On the left side we have only the Ax term. So take only the it is Ay term. So Ay term is there on the left side. So write dou Ex by dou Z Ay is equal to minus dou by dou T By into Ay. So remove the unit vector terms. So this is the left, and in place of B we can write B is equal to mu into H. So write mu H and substitute in this equation. So we get this as the final equation. Now we'll start with the first equation which we got earlier. So this was the first equation, dou Hy by dou Z is equal to this term. Now differentiate this first equation with respect to t on both sides. So partially differentiate this with respect to t. So write dou by dou t and dou by dou t here also. So here we get dou square Hy by dou t into dou Z. This side we have minus epsilon dou square Ex by dou t square. Now again take the second equation, this one, and differentiate this with respect to Z on both sides. So write dou by dou Z, here also dou by dou Z. So we get dou square Hy by dou t dou Z is equal to minus 1 by mu dou square Ex by dou Z square. Now if you see this third and fourth equations, what is similar here? If you see the term on the left side, we have dou t by dou Z, and in the numerator we have dou square Hy. So the left side terms of both of these two equations are same. So we can equate the terms on the right side. So we have this minus epsilon dou square Ex by dou t square is equal to minus 1 by mu dou square Ex by dou Z square. So remove the negative sign on both sides. And if you solve this second order differential equation, so this is the solution we get. Ex is equal to Em plus cos omega t minus beta Z plus Em minus cos omega t plus beta Z. So the other equation solution can be written as Hy is equal to B by mu omega Em plus cos omega t minus beta Z minus beta by mu omega Em minus cos omega t plus beta Z. So this whole term we can write it as Hm plus cos omega t minus beta Z minus Hm minus cos omega t plus beta Z. So these are the two uniform plane wave equations. Next topic is the wave equation in the phasor form. Again we need to start with the same equation, that is the Maxwell's equation. Del cross E is equal to minus dou B by dou T. Now apply curl on both sides, that is del cross E is equal to del cross minus dou B by dou T. Now you can use the vector identity, that is del into del dot E minus del square E is equal to del cross E. So in place of this del cross E we can substitute minus dou B by dou T. So in place of B write mu H. So this becomes minus dou by dou T into mu H. So put mu aside and write dou by dou T into del cross H. But we have another Maxwell's equation as del cross H is equal to J plus dou D by dou T. So in place of this del cross H write J plus dou D by dou T. And if you consider any medium without free charges like free space or dielectric, then del dot E term will be equal to 0. So this term, the first term on the left side becomes 0. So these are the terms left. Minus del square E is equal to minus mu dou by dou T J plus dou D by dou T. Now here we can use a substitution. dou by dou t can be replaced with j omega if the field varies with respect to time. So put j omega in place of dou by dou t and simplify this equation. So we get del square E is equal to j omega mu into j plus j omega epsilon into E. Either you can stop it here or still simplify by substituting j is equal to sigma E. So this is the point form of Ohm's law. So substitute, simplify, and in place of this whole equation j omega mu sigma plus j omega epsilon, in place of this whole expression we can put gamma square into E. Here gamma square is the same equation, and if you want gamma, put under root for this. Now if you take another Maxwell's equation, that is del cross H is equal to j plus dou d by dou t, and proceed everything as in the previous derivation, we get the equation in terms of H, that is del square H is equal to gamma square into H. So here gamma is known as the propagation constant, which is equal to alpha plus j beta. Here alpha is attenuation constant and beta is the phase constant. We will see what is this attenuation constant. What is meant by the attenuation constant? Attenuation means whenever the distance is longer, the amplitude of any signal reduces. So the reduction in the amplitude of the signal, we call it as attenuation, and it is expressed in Newtons per meter. Then we have the beta or the phase constant. So if there is any phase change in the transmitted and the received signal, we call it as the phase difference or the phase constant beta, and its units are radians per meter. So you can see the signal for the attenuation constant. As the distance increases, the signal strength or the amplitude decreases. That is attenuation constant. And if this is the transmitted signal and if this is the received signal, you can see the transmitted signal is starting at this point 0, that is a sine wave, and the received signal is a cosine signal. So there is a phase difference of 90 degrees or pi by 2. Next we have another important term, that is the intrinsic impedance, denoted by eta. So this is the relationship between eta, E and H. This is also equal to j omega mu by sigma plus j omega epsilon. So this equation you must have come across somewhere in transmission lines. So directly this equation was taken from there. In the previous wave equation derivation, we have used the substitution where Hm is equal to Em beta by mu into omega. So in place of Hm, substitute this whole equation. So we get omega mu by beta. Another important term is the velocity of propagation. So this is denoted by the small v, which is equal to omega by beta. So this was equation also you got it from physics. So velocity of propagation also can be expressed in terms of permittivity and permeability. That is 1 by under root mu into epsilon. So intrinsic impedance, in place of this omega by beta, substitute the velocity of propagation. So we get mu by epsilon under root. If we take the intrinsic impedance of free space, so in place of this mu and epsilon, we can write mu naught and epsilon naught, and put the values of these two constants and simplify. So we get this is approximately equal to 377 ohms. Similarly, the velocity in free space. So you have seen the equation for velocity of propagation, 1 by under root mu into epsilon. So if you take the free space, mu and epsilon can be replaced with mu naught and epsilon naught, and substitute these constant terms So you get this value 3 into 10 raised to 8 meters per second. So the next topic, we have uniform plane wave in a perfect dielectric. If a medium through which a uniform plane wave is propagating in a perfect dielectric. So a perfect dielectric also means a lossless dielectric. So in a dielectric or a perfect dielectric, the sigma, that is conductivity, will be equal to 0 and permittivity will be equal to epsilon naught into epsilon r, and mu is equal to mu naught into mu r. Again use the equation for propagation constant, j omega mu into epsilon plus j omega sigma plus j omega epsilon. So in place of this sigma, substitute 0, as the conductivity in a dielectric is equal to 0. So put 0 in this place, so we get j plus or minus j omega mu into epsilon. So if you see this equation, we don't have any real term, only the imaginary term is present. That means in a perfect dielectric, the attenuation constant alpha is equal to 0. Now write the equation for propagation constant. Gamma is equal to alpha plus j beta, and equate it to this term which we got just now, that is plus or minus j omega mu epsilon. So if you remove the j term on both sides, we get beta is equal to omega into under root mu into epsilon. Next we need to solve for the intrinsic impedance in a perfect dielectric. Again use the same previous intrinsic impedance equation, j omega mu by sigma plus j omega epsilon. So in place of this conductivity, substitute 0. So we get mu by epsilon under root. Now here if you see, there is no j term. That means there is no imaginary term. Only the real term is present. So what does this mean? The intrinsic impedance is purely resistance term. Okay, there is no capacitance or any inductance term. That means the phase angle is 0. That means E and H are in phase with each other in a perfect dielectric. Again we need to solve the equation for velocity of propagation, that is 1 by mu epsilon under root also equal to omega by beta. Now you need to solve some problems also based on this. Then we need to solve for the uniform plane wave in a perfect conductor or a good conductor. So if you see, a good conductor means it has very high conductivity or maximum conductivity. So this is the value for copper or aluminium, that is a conductivity 10 raised to minus 7 mhos per meter. So we can use this substitution here, sigma, which is the conductivity, is a much larger value compared to j omega epsilon. So take the equation for gamma, which is alpha plus j beta, j omega mu into sigma plus j omega epsilon. Now here sigma, that is the conductivity, it is a very high value, so you can neglect the other term, that is j omega epsilon. And simplify this, we get omega mu epsilon into under root of j. But under root of j means it is equal to angle of 90 degrees. So in place of this j, put the angle of 90 degrees, remove the under root, we get angle of 45 degrees. So this can be written as cos 45 plus j sin 45. So write both of these two values, we get 1 by root 2 plus j 1 by root 2. So in place of omega, substitute 2 pi f. And we can cancel this root 2 in the numerator and denominator. So these are the terms left. Now compare this equation with the propagation constant, which is equal to alpha plus j beta. So alpha is equal to under root pi f mu epsilon Nepers per meter, and beta is equal to pi f mu into epsilon radians per meter. So if you see, both of these terms are the same. So what does that mean? That in a good conductor, the attenuation constant and phase constant are equal. Next, we need to solve for the intrinsic impedance in a good conductor. So follow the same procedure. Follow the same procedure, and in place of sigma, substitute 0 and simplify. So we get this equation. Next, we need to solve for the skin depth. This is a next new term here, skin depth. So whenever any wave propagates in a good conductor, so earlier we have got that there is a zero attenuation is equal to maximum in a good conductor. That means there is no phase constant, there is only attenuation in a good conductor. That means the signal cannot propagate in a conductor. So any electromagnetic wave, it enters into a conductor, but after a certain distance it gets attenuated. So if you see in this signal, this is the point at which the electromagnetic wave is entering inside a conductor. So initially we have taken z is equal to 0. Initially the amplitude is a large value of Em, but as the wave passes through the conductor, you can see after certain point the amplitude is reduced by a certain factor. So this factor is e raised to minus alpha into d. So if you substitute alpha is equal to 1 by d, so we get e is equal to Em e raised to minus alpha into d, which is Em. Put 1 by alpha in place of d, so these two are cancelled. We get Em e raised to minus 1, that is 0.368 Em, that is 37% of Em. So why we have taken this equation Em e raised to minus alpha d? So if you see this waveform, it is decreasing exponentially, that is the amplitude of this wave is decreasing exponentially, and its initial amplitude is Em. So for a decreasing exponential wave, we use this equation e raised to minus alpha into d. So that's why we have used the same thing there. So we get this as 37% of Em. That means this is the distance, that is the skin depth is the distance at which the amplitude of the wave decreases to approximately 37% of its original value. So for a good conductor, alpha and beta are the same. So d is also equal to 1 by alpha, which is also equal to 1 by beta. So this is the expression we got for alpha and beta. So we can write the skin depth in a good conductor is also equal to 1 by pi f mu into sigma meters. Next we have relationship between the electric field intensity and the magnetic field intensity. So we know that the E and H are perpendicular to the direction of propagation of the electromagnetic wave. So here also we use the Maxwell's first and second equations, expand on both sides as we have done in the previous derivations. Use the cross product expansion and reduce Ey and Ez to zeros, and E varies with respect to Z only, so other term also becomes zeros. So this is the equation we get here. Similarly expand on the right side also. So this is the final equation which we get here. Dou Hy by dou Z is equal to epsilon dou Ex by dou T. Now here we need to use one equation from physics, which is Ex is equal to F into Z minus Vt. Let us suppose this is equal to some capital F. Here small f is the frequency of propagation, this V is the velocity of propagation, and T is the time, and Z is the direction of propagation. Now differentiate this equation with respect to time. So we write dou Ex by dou T is equal to F dash into, here F dash is the differential dou f by dou t. So put dou f dash z minus vt and dou by dou t of z minus vt. So differentiate this, we get v minus v f dash z minus vt, or we can write this as minus v into capital F dash, where this capital F dash is equal to small f dash into z minus vt. So this prime on f indicates that is the first partial differentiation. Now again take the second equation and follow the same procedure, equate it to minus v into f dash. Dou hy by dou z is equal to epsilon v into f dash. Now take this equation and integrate on both sides. Take this dou z also this side. Now integrate, we get hy is equal to epsilon v f plus k. Here k is the constant of integration which can be neglected. Or hy is equal to epsilon v into f. So in place of v, put 1 by mu into epsilon into f. Or simplify this, we get epsilon by mu into ex. Or take ex, hy and ex you take on one side and these terms on the other side. So we get ex by hy is equal to mu by epsilon under root. So this is the relationship between E and H, where E is along the x-axis and H is along the y-axis. This is the next topic, electromagnetic wave propagation in different media. So for free space, we need to write the conductivity is equal to 0, epsilon is equal to epsilon naught, mu is equal to mu naught. In a perfect dielectric, epsilon is equal to 0, sigma is equal to 0, epsilon equal to epsilon naught into epsilon r, mu is equal to mu naught into mu r. And if you take a lossless dielectric, sigma is not equal to 0, but it is a very small value. Epsilon is equal to epsilon naught into epsilon r, mu is equal to mu naught into mu r. And if we take a good conductor, sigma is equal to infinity, epsilon is equal to epsilon naught, and mu is equal to mu naught into mu r. So these are all the topics in this first half of the electromagnetic wave characteristics. Thank you for watching.